So now you've watched those two videos on what the difference is between transverse and longitudinal waves. We're going to make some notes on these two to go into our books. Now I'm going to go through them a couple of times with a couple of different kind of animations. You just need the definitions down. I will explain it as we go through exactly what you need in your book, but hopefully doing this in a multiple kinds of ways will help your understanding of exactly what is happening. So you should know now that we've got two types of wave. We've got a transverse wave up at the top here, and we've got a longitudinal wave down at the bottom. The big difference is this one looks, so my transverse waves looks like a standard wave that we normally think of. A longitudinal wave, you'll notice it doesn't move up and down or perpendicular to the motion. It's moving parallel to the motion, and these single objects are moving parallel, so in that same kind of direction. If I look where the laser pointer is pointing and I look at these individual parts of this spring, so as this wave comes through, it goes up, down and back to the center. You'll notice in this transverse wave, my slinky does not move side to side at all. It moves up and down whilst my energy is moving to the right. For my longitudinal wave, each section of this spring bounces in between like around a fixed position, and this is what was meant here. So we've got part of the waves oscillate, and that word is going to come up again and again throughout this topic. And oscillate means to vibrate, so it moves one way then the other, and then it moves back to where it kind of started. All right, so if I'm oscillating around the point at the moment, it go one way, back the other way, and then come back and stop where it started. All right, so that's oscillation. It's a vibration between two kind of points. Now, the parts of the wave never move far and they never permanently move, but energy passes through them, which allows them to pass it on to the next part of the wave. So we're going to look at these in a little bit more detail. So you need this little subheading of transverse waves. You need this diagram right in this example. Okay, but each individual part of my wave is moving up and down. So as it reaches where the laser pointer is here, this part of the wave will move up and down and up and down and up and down as long as the energy is passing through. So the part of the wave is moving perpendicular to the direction of that motion. That's our really important definition. This is one that you have to know off by heart. So get it into your book, highlight it, whatever you box it, whatever you need to do to make it stand out in your notes. But this is something that you absolutely must learn. So transverse waves have oscillations. Perpendicular is the key word here. So perpendicular to the direction of motion of the wave, or perpendicular to the direction of transfer of energy. So the way the energy is going one way, the wave's going one way, the particles are moving perpendicular. If you need to pause the video and get those notes down, do so. The final thing that we need to add at the bottom here. So what types of wave are transverse wave? Well, this looks like the waves that we normally get on the top of a pool, like a ripple. All right, so if I threw a stone in, I would see this kind of wave on the top of water. So we've got transverse waves. We've got light. Okay, so light that enters your eyes looks like this. Water waves, so ripples, etc. They're transverse waves. And here is a distinct difference that you need to know. So the secondary waves produced by an earthquake. All right, and we refer to these as S waves. A handy way to remember this is if I turn that S on its side, it looks like a transverse wave. All right, so let me just grab a pointer, my pen. So if I turn that S on its side, it looks like my transverse wave. So it's a nice, easy way to kind of remember exactly what that looks like. Now, it's a secondary wave produced by an earthquake because there's one that happens before, and we're going to look at them in just a second. This next piece of information is probably the most vital that you're going to need. So all EM waves, and EM stands for electromagnetic waves. Okay, so electromagnetic waves, all of those are transverse waves. You need to write that fact down, and that needs to stick out in your notes more than anything else. So all electromagnetic waves are transverse. We are going to be focusing for about 3 or 4 lessons on just these electromagnetic waves later in this topic, but you need to know that they are all transverse. Now we come to this idea of longitudinal waves. All right, so this is a different kind of wave type. Longitudinal waves have oscillations parallel to the direction of motion or the transfer of energy. So in this example, my energy is transferring from left to right, and you'll notice that each part of this spring or slinky is oscillating parallel to that motion. So the energy is traveling from left to right, and also these are vibrating left to right as well. Okay. Now we've got compressed and extended parts where we've got bunched up areas of my slinky and spaced out parts. Okay, so the first thing that we need to know, when they're squished together, nice easy name to remember, we've got compression. All right, so those are areas of compression. This one is more difficult. I very rarely get anybody that knows this term before, but the spaced out areas, and again you need to know this name, is rarefaction. Okay, so rarefaction is the areas where it is spread out. So you need to know those two parts. Examples of these types of longitudinal waves, sound waves, which we're going to do a lot more detail on as we go, and the primary waves produced by an earthquake. And we call these P waves, P for primary. You'll notice that the other ones were secondary waves, S for secondary, these are P for primary. All right, so you need to know the difference between those two. If you have any questions at this point, pause this video and come onto Teams and ask me. If there's something that you need to ask, come onto Teams and ask me, because if you haven't quite grasped this first bit, the rest of this topic is going to be much, much more difficult. Again, we're just going to run through this in a slightly different fashion. So our wave travels away from the source. The direction of the wave is at right angles or perpendicular to the moment. So this is a transverse wave. And you'll notice my source moves up and down. My wave is traveling from left to right, and my coil vibrates up and down. It's not moving left to right. So that's a transverse wave. Just another example, another way of looking at it. If you want to pause and copy down this diagram as well, I strongly suggest that you do. And for longitudinal waves, we've got another diagram. Source moves left and right. The wave is moving left to right, and the coil vibrates left and right. So these are parallel to each other. So it's the vibrations and the direction of that wave are parallel to each other. They're in the same line. Now, quite a lot of information to take in so far. Okay, I now want you to draw this diagram into your book. It should be at least half a page, and if you want to go landscape and do this as a whole page, that is absolutely fine by me. Make sure, and these are really key points, these should be at the same height above this line, and that should be the same as the height of these from this line. So this distance from the middle should be the same as this distance from the middle. The other thing you need to make sure is that they are evenly spaced. So this section for this part of the wave is the same distance as this, is the same distance as this, is the same distance as this. What I would do to help you draw this is draw 1, 2, 3, 4, 5, draw some crosses so you've got the widths are even, and then try and draw a line across, or draw some crosses across at the same height, maybe using a line in your book, and then draw in your wave. Okay, that might make it a little bit easier. So pause the video, get that done now. Okay, hopefully you got that into your book, and you hopefully will know how to measure the wavelength and what the amplitude of our diagram is. So these are some points to kind of add to your book. We have the wavelength. Okay, so one whole wavelength. Now we can go, and I'm just going to change over to a pen here, and I'll make a point of labeling these. So these tops of our waves are called peaks. Okay, so they're peaks up at the top. And you may know that down at the bottom, we call those objects troughs. All right, so they're points that you can label onto your diagram. So we've got peaks up at the top, and every time I'm down at the very bottom, I'm in a trough. Now, one wavelength tells me that I have completed one whole wave. So this is a really kind of important definition. Now, if I look at this diagram, if I start at the top of this wave, I travel down here and back up to the top of these peaks. So I've done one complete wave because I've now moved over to the same point on the next wave. So this must be one complete wavelength. All right, so we've got one whole wavelength. If I started at this point, what I want you to do is tell me where one whole wave ends from this point here. Okay, so pause the video, think about where one whole wave ends from there. Okay, and we can have a look at this. So we've got one whole wave. I'm going to come up to the first peak, down to the trough and back and end at this point here, because this is where the next wave starts. Okay, so I've got, that is one whole wavelength. Okay, if I started in this middle part, I would go down, then up and down, so I'd have one complete wave. So it doesn't matter where I start and measure from. I could even start here if I like, but I need to go to the same point on that next wave, and that will give me one complete wavelength. Okay, so it's just from the same point on the first wave to the same point on the second wave is one complete wave. And what we're talking about with wavelength up here is how long the wave actually is. So how long does it measure? So this could be 10 centimeters in total. So the wave is 10 centimeters long, or it could be a millimeter. It could be a very large wave, like a radio wave, can be multiple meters, so 10 meters or so. Okay, so it's just something to think about as we go. So a wavelength is the length of one complete wave. The other value that I need to know is amplitude. So the height of a wave above the zero line. So you'll notice that this value here is your amplitude. And the other thing that you'll need to notice is the amplitude. And let me just change my color so you know we're talking about amplitude instead. So I'll go for a purple. So I've got one amplitude here. And notice it's from a peak, not down to the trough, but down to the center line, so the zero line. Okay. Where else could I kind of label my amplitude on? Well, I could label it here. So this would be my amplitude of my wave. Okay, so it's the maximum displacement from zero. And you should notice this amplitude should be exactly the same. So this amplitude here should be exactly the same as the amplitude up here. Okay, so it is from zero, the middle line, to the peak, or from the middle line, the zero, to the trough. The biggest mistake that people make here is thinking it goes from peak to trough. That is not the case, and you will lose marks if you think that at your GCSE. Okay. Now, the final thing that I will add, and again, I'm just going to change my ink colour so you know we're talking about something different, is sometimes this graph is in meters. Okay, so I'm measuring displacement. Okay, and we've done displacement. It's how much the wave moves from my center line. Now, if this is in meters, this value, this red value, gives me a wavelength. So it tells me how long my wave is. Sometimes, though, they put this graph in displacement against time. And when this is in time, what I can work out is the time it takes for one wave. So time for one wave. And we call that the time period, which we're going to be using quite a lot this lesson. So the time for one complete wave is a time period. Okay, and we're going to do a little bit more work on that next. Make sure you've got all these notes down in your book. If you haven't, pause it and then move on to the next slide. Now, we need to understand this idea of frequency. Okay, so we've got this idea of frequency. Again, a little subtitle is going to help you here. Frequency tells us the number of waves per second. So how many waves there are every second for my object. It comes with a very simple formula. Okay, and that formula, oh, there we go, there's our unit first. So this is measured in hertz. Notice this must be a capital H and a little z. Okay, for our unit. So it's measured in hertz. And our formula, again, needs to go down into your book, boxed, highlighted, whatever you want to do. But frequency is 1 divided by my time period, and my time period must be in seconds. Okay, so the time period must be in seconds. If they give you it in milliseconds, etc., you have to convert it and make sure it is in seconds instead. So I've got frequency is 1 divided by my time period. Frequency is 1 divided by t. That tells me how many of them there are in 1 second. What I want you to do now is pause the video and answer these 2 questions. So pause this video and answer these 2 questions. Okay, so we're now working on a sound wave with a time period of 0.001 seconds. What's its frequency? Well, I'm going to use my formula that we've just learned. Frequency is 1 divided by the time period. So 1 divided by 0.0001, which is going to give me an answer of 10,000 hertz. Some of these hertz are going to be exceptionally large numbers. Okay, don't be put off by that. Some of them are going to be millions, if not more. Okay, so hopefully you got that one right. If you didn't get that one correct, come on to Teams and ask me. This one required you to do a bit of rearranging. Okay, so again, I can do F is 1 divided by time. If I fill in my numbers, 8 is 1 over time. And then I can start to rearrange this formula. So 8t equals 1, and then t equals 1 divided by 8. Okay, which gives us a final value of t is 0.125 seconds. So learning to rearrange this formula is going to be really important. Final new piece of information today. Okay, and we're going to do quite a lot of practice on this from this point on. So we're going to look at this idea of the wave equation. So all waves, doesn't matter whether they're transverse or longitudinal, follow the same equation. This is a very simple formula. I can absolutely guarantee this formula will be on your GCSE. Okay, it's such a common question. It will be on your GCSE at some point. So we have this formula, velocity equals frequency times wavelength. Okay. Velocity is frequency times wavelength. I'm going to introduce these little symbols. So velocity is little v, same as before. Frequency is little f. All right, we've looked at that before in our previous formula. But then we've got this idea of wavelength. So we've got this symbol, and this is called a lambda. And I'll write that onto the screen for you now. So it's spelt lambda. Okay, it's an old letter from, I think it's the Greek alphabet, etc. But it's almost like an upside down Y. Okay, so it looks like this, and that is a symbol that you will see. You need to learn that that means wavelength because they don't tell you that in your GCSE. Now, let's kind of put some extra information here. So V is wave speed, and that is measured in meters per second. The frequency is measured in hertz. We did that just a second ago. And wavelength, again, must always be in meters. So my wavelength must always be in meters. So make sure you have got that written down into your book. Even this part down at the bottom needs to go into your book. The one thing you must remember is these units are really, really important. This must be meters per second, this must be in hertz, and this must be in meters. They often try and catch you out with those by giving you it in kind of centimeters or millimeters. You need to convert it to meters. Make sure this is in your book with all your notes. If a wave has a frequency of 40,000 hertz and a wavelength of 0.75 meters, okay, so we're going to just use this formula very simply. So velocity equals frequency times wavelength. So we've got a frequency of 40,000 hertz. There's my wavelength, 0.75 meters. The speed of my wave is going to be 30,000 meters per second. And again, don't be put off by these large numbers. Some of these waves travel incredibly quickly. What I want you to do is rearrange that wave equation. So take that V equals F lambda equation and rearrange it. So F equals, and then rearrange it again. So lambda equals. So pause the video, do that now. Okay, and what you should see as we go through, we should have frequency is wave speed divided by wavelength, and lambda is wave speed divided by frequency. So those are your two other formulas. Jot them down. You should be able to rearrange this formula no problem by now. And I want you to pause this video and attempt these 3 questions. Okay, make sure that you are paying attention to the units. So pause the PowerPoint now, attempt these 3 questions. Remember, I want to see formula, number, answer, unit. Off you go. Okay, so once you've done those 3 questions, we should have an answer for the first one, 1500 meters a second. That should be fairly simple. We've just got that frequency, 500 times wavelength of 3, 1500 meters a second. A ripple on my pond, I'm multiplying these together. Luckily, this is in meters here, so I'm paying attention to that. Should give me 0.8 meters per second. And a radio wave, 30 meters and 10 million hertz. Now this comes out as 300 million meters per second. And that is 3 times 10 to the 8 meters per second. You should recognize this. And this number is the speed of light. Okay, so speed of light. Now that is going to come up a lot in this topic, because remember earlier I talked about electromagnetic waves. All electromagnetic waves travel at that speed of light. So all EM waves are going to travel at that speed. And again, that's a fact that you need to know. We're going to do it again in a couple of lessons time, but make sure you're registering that in your brain already. Okay, we're now going to use a kind of rearranged version of that formula. So again, pause this PowerPoint, attempt those 3 questions. Okay, welcome back. So hopefully we've got these 3 answers. So we should have 1.5 meters. We've got our wave speed divided by frequency, 3/2. Ultrasound wave, again, we've got wave speed divided by frequency to calculate wavelength. So 1450 divided by my 40,000 is 0.036 meters. And finally, wave speed 340 divided by frequency 440 gives me a value of 0.77 meters or 77 centimeters. Okay. Finally, we're going to do some calculations for frequency. So again, pause this video, attempt these 3 questions. Okay, so we've got a sound wave. Again, our formula for frequency now is wave speed divided by wavelength. So 340/10 gives me my 34 hertz. Wave speed, 8 meters a second divided by my wavelength of 20 gives me 0.4 hertz. And a microwave of wavelength 0.15 meters. So I've got that again, the speed of light, 300 million meters per second divided by my 0.15. gives me 2 billion hertz. Okay, and this is not an irregular number here. We should have 2 times 10 to the 9 in standard form. You're going to have to get used to this kind of idea of standard form. Now, does anyone know what I can also call this times 10 to the 9? Hopefully, you might recognize this. So that will be 2 gigahertz. Okay, so kilo is 1,000, mega is 1,000,000, and giga is my billion value. Okay, so you might need to know those a little bit later on. If you get stuck, if you see a symbol that you don't recognize, you can type it into Google and it will give you a kind of answer about standard form. So on the worksheet you're about to do, you will not recognize some symbols. Okay, so there's going to be a few of them. I'll give you a clue. So you've got micro up in the top right, means 1/1,000,000th. Okay, so we've got I'll tell you what, I'll do this in standard form. So 10 to the -6. Milli, like millimeter, is 10 to the -3. Okay, and we've got nano is the small one, times 10 to the -9. We'll go through these multipliers again at some point. Again, look them up online. If you want to look them up, you can call them multipliers. So if you type in multipliers physics, they will come up for you nice and easy. Finally, we're just going to do this question together. Okay, so I want you to look at these two graphs. I want you to pause this video and give this question a go. So all 3 parts of this question, give this question a go. Pause the video now. Okay, so we're just going to look at how to answer this type of question. All right, so the graph below represents displacement. Okay, find the amplitude. Well, we said our amplitude was from here to here. So our amplitude, we read it off of our graph, is 10. And look at this unit, millimeters. So answer for part A is 10 millimeters. And you'll notice that your answers are coming up on the right over here. Now, I want to find the wavelength. Well, I need the length of one complete wave in that case. So I'm going to come up and down, and it's this point here where I start a new wave. And if I read this off, I've got 4 millimeters. So 4 millimeters is my total wavelength, because it's the length of one complete wave. Don't be confused and think it's 2, because that's not one wave, that's only half a wave. For number 3, or 2, part A, well, I'm measuring amplitude. Again, it's for the same wave, so it's from there. I read it off. I've got 10 millimeters. If I look at the time it takes for one complete wave, and notice now I'm measuring time on my x-axis rather than distance on my x-axis. So now I can read off my time period. So time for one complete wave, 0.5 seconds. And the third part of this question, I'm asked to calculate frequency. I've got my formula, F equals 1 divided by T, which gives me a frequency of 2 hertz. 1 divided by 0.5 is 2 hertz. Final question, part 3. Use your results from question 1 and 2 and calculate the speed of the water wave. Okay, well, I know V is F lambda, so I can put that on there. I've worked out F, I've worked out lambda, so I can do my values. And notice I had to convert this into meters. So I had to change it from millimeters into meters. Velocity is 0.008 meters per second. Now it is your go. Okay, I have attached a worksheet that you are going to need to work on. Okay, you can do that off of the computer, go away, use your calculator, make sure you are being very, very careful. Now, you need to be exceptionally careful about units. There are lots of tricks on this worksheet, so you need to make sure all of the units are in the units that they need to be. Convert everything to seconds, convert everything to meters as you go through. Okay, and then you're going to get the kind of right numbers. Once you've done the worksheet, okay, so you should be able to calculate those values as you go through. So calculating those values. Once you complete, if you go on to show my homework, there is a quiz. And on that quiz, there is multiple choice for the answers for your questions. So it's the worksheet you are doing, but then you're going to go on and you're going to put in your answers for 1A, 1B, 1C, etc., all the way down to question 5. So that will allow me to see how much of today's lesson you have taken on. Okay, so that is your task. Make sure you complete that show my homework task. It's really, really important that you do. Finally, I'm on Teams, so if you need anything at all, come and ask me, and then we can go from there. If we need a little bit more explanation, if you need anything at all, come on there and ask me a question. Looking forward to seeing you soon, and good luck with today's work.